this, because the R is so much bigger than D.
If the theta is, because what you're doing is getting the dot product, right? Essentially of
Yeah.
of the moment and the, or no, P and the moment, right? Is that what I'm saying, right? So it would be that if it was that other angle, then cosine theta would be way closer to 0.104, because it would be closer to, it would be a smaller number, right?
D has to be much smaller.
Which it was in the test.
As D gets smaller, it's going to have less of an effect. It'll have an effect on this, but it's going to have less of an effect on this than it will have on this.
Right. Because if R is way bigger than D, then they're essentially parallel coming off of that.
Yeah.
So wouldn't it?
Like I said, I just thought it was fascinating because I didn't off the top of my, I thought I picked a value that was close enough that it would work. But I didn't want numbers that were so close to zero that it was basically a rounding error to get zero. And so I was trying to keep it reasonable, but it just didn't, kind of didn't work out that way.
Because if I remember from the test, because I calculated the angle between the direction of the dipole moment and then the line coming off the center, and the angle there was like 89.98 or something like that. So if I use the other angle,
89?
yeah, it was basically
It's pretty much 90
because
degrees.
it was 0.25 meters and like 0.01 or something like it was.
No, 1.5 times 10 to the negative, 1.5 times 10 to the negative 4.
Yeah.
So there was like 1
Yeah, so
into
even smaller.
1 into 100 at best.
Right. So it was way bigger than the little
Or
D
1 into
here.
200.
So it was basically
one.
looked at as 90 degrees.
But
down.
the rounding error,
Right, but if
Yeah,
I'm saying that
it's
if I
just
used
crazy.
the theta on the one that's up there, it would have been 0.02 degrees. That's my theta in the equation. So wouldn't that make a quite large difference?
well, the problem is, all that does is make this look closer to 1, so that you can more cancel this, eliminate this term under that condition. And the problem with that is if this is just 1, give or take, then it all breaks down to how this ratio looks. And if you just calculate this number, it comes out to something like 34. You've got 9 times 10 to the 9, 2 times 10 to the negative 10, and then you're dividing by 0.25 squared, so you're going to multiply it by 4. So you're going to get a number that's in the 1s to 10.
Okay.
So, yeah, I don't know, I was just very interested. I don't have an answer for it off the top of my head. I'll probably look at it after class, but as I was just going through some of the exams, I was quite surprised. No. Yeah. I'll change. It's nice to get this little tighter title in. In fact, I think, did I bring mine? I did bring mine. So ultimately, the idea is now as we make a step in a different direction, I need to think about this and see if I can say this in 2 minutes. When you have individual electric charges, they produce electric fields. But when you observe a charge moving, the electric field will move due to the movement of the electric charge. Or let me say it a different way, the electric field will change in space and time as the charge moves along. Well, when you observe that changing electric field, we observe it as what we call a magnetic field. So the connection is not directly obvious, but what it comes down to is when you have a changing electric field, you get an observed magnetic field. And when you have a change, and by inference, you might sort of make the postulation, if you have a changing magnetic field, maybe you ought to get an electric field as well. And that'll be the last thing that we talk about at the end of the quarter. But ultimately, this is fundamental. It's the second aspect. Charges produce electric fields. Moving charges and those changing electric fields have associated observable, what we call magnetic fields. So ultimately, that's sort of the foundation, is that charge movement of any kind results in a magnetic field, what we call a magnetic field. Now, this is what's sort of odd about it. You take a charge, and just think about this thought problem. Some of these things, it's just, man, it just doesn't seem right. It's a complete relative thing. Okay? Part of the idea of Einstein's theory of relativity has to do with the discrepancy between this idea and Newton. And the idea was something like this. If you say you have a point charge, I'm just watching this point charge, and I'm just holding it and say, okay, I got this radioelectric field. Good enough. Well, what does that same electric field look like to a car driving by in their reference frame? It looks like a magnetic field. And that's what's freaky. It's relative motion. There's no such thing as rest, right? Motion is a purely relative to observation. So if you're looking at what is ostensibly a non-moving charge, it's only not moving with respect to somebody watching it in the same reference. But if you cruise along, so here's my charge, and I got two people watching it. I got somebody standing here watching this thing and saying, okay, well, out here I've got an electric field. I guess I should draw it that way. That's due to this thing, right? Well, and that would be the same in all directions. Now I have a car coming by and somebody in the car. Okay, I know, that's a perfect person in a car. And this person says, I want to look at the same distance away. What's the electric field here? So in other words, it's looking at space. He's looking at space, or she's looking at space in their reference frame. Well, the problem is, as a car goes by, this point changes relative to the charge, because from this person's observation, it's as though the charge is moving in this direction. So at this point in space, which is stationary to this driver, this person sees this time-changing electric field, which is observed as a magnetic field. So we got all these relative, funky relative relationships that do nothing more than to observation, how you're looking at it. Okay, so one person's electric field, say, well, it's hard to draw, but at the same distance away from the other will give you a completely different answer. And so it's bizarre. Now, to this end, then, it's hard for me to draw this, and you've got some words you can figure it out. First of all, we typically write the magnetic field as a letter B. Now, the fact that magnetic fields are fundamentally produced by changing electric fields has interesting consequences. Because if it's changing in an irregular fashion, it's going to produce a magnetic field that itself will be changing. And the changing magnetic field, in turn, will be observed as a changing electric field. So when we talk about the flow of light waves, it's fundamentally the symbiotic jostling or oscillations of electric magnetic fields.
Does that mean they would have a similar relationship as kind of like waves? Like you take if you look at how that changes, what's like the next portion, if you give it back, it looks like the original a little bit.
In a sense, yeah. To just sort of conceptually put it this way, if you had an electric field that were changing like this in time, then you would observe simultaneously the rate of change of this thing is going to be related to the observed magnetic field. And so that magnetic field would look something like this, which would be out of phase. I'm not going to worry about the magnitude of this thing, but would be out of phase the electric field. And it's these changes that ultimately disturb and interact with the space around it. And you get this self-perpetuating light experience, if you will. So it's a crazy thing. But to begin with, as we approach it, we're going to look at two different ideas. So when you have charge movement in wires, seeing a long straight wire, I've got a current flowing through this thing. And that would be because I got a plus or I got a minus